All right, good morning, 150 people. I'm back here in my little closet. It seems to work okay for these sessions, and this is becoming the new sort of temporary normal for me. I'm getting used to it. We've had good interaction. Most everybody got through that exam okay with pretty good results on that. So things are working, getting work back and forth. I put out Monday the work for this week and the lab, and we got questions on trigonometry. We got a lot of sections in 1 week here because hopefully got some background in trig to work with. Usually people come in with varying degrees of knowledge about trigonometry, so this might be super familiar to some of you and less so to others. So I don't know which parts of it you're going to have questions, concerns about. Hopefully you tried some of that stuff out, and hopefully this video will help. If you can drop in some comments of which ones you're having issues with, that would help me. I'll try to keep an eye out for questions as we go through the week too. Bunch of chapter 6 homework questions. I have the book handy. We can look at some of those. And then the lab kind of answers. The lab kind of asks some strange questions. The way that it's phrased on there and the way that you're looking at things on there about the graphs and trig functions. So I'll probably work through some of those as examples here also. So I hope this will be helpful. In that way, I will try to get this thing set up, work some exercises in here. Hope things are going okay for you. If technology is getting in the way or other things in life are getting in the way of you being able to succeed in this work, college is trying to mobilize resources and help people out. We know that nobody's getting kind of what you signed up for this semester. We want to make the best of it and see that people have the support that they need. And there's been some technology assistance coming down from the SUNY system too, who's trying to help everybody throughout the state. So if you got hangups with technology or other areas of life, I have some contacts on it. You can get a hold of the college or let me know what's going on, and I have some connections I can try to point you to get some help with that. If you're just having trouble with pre-calc, then I can help you with that. Certainly drop the questions in here during this time, or if you're watching this later, drop some questions into the email or the Blackboard discussion group, and I'll get back to you that way, or put some more videos up later if I need to. Let me try to get going with some of this work for now. Sine, cosine, and tangent functions and all of that in a pre-calc context. So we're thinking more about the graphs of these things. I have algebra sitting here. Try to work on some straight white paper and see how that goes today. The graphs of the functions. So trig functions. And if your native way of thinking about trigonometry is having to do with triangles, that is what trigonometry means, but not the greatest way to think about them right now. So we have to get beyond that. The triangles are still applicable, but I want you to be able to think about these things in several different ways. And having graphs of the trig functions be a natural way for you to think about sine, cosine, and tangent is in terms of the function graphs. That's going to be really important going forward into calculus, of course. That's the main thing that we do in pre-calc is get used to the connections between the graphs and the equations of stuff. So with trigonometric stuff, we're going to have these kind of graphs. And how these things end up looking on the graphs is pretty important. So I want to get working on that. way of thinking. So I'm going to try to interpret the problems that we do in a couple of different ways to get used to unit circle thinking and to get used to the graphs of the functions thinking, and how to interpret each of these sort of facts or ideas in both of those ways. It's really kind of important. My own little journey on this is a little weird. My own personal story for getting through trigonometry. I placed into Calculus 1 when I got to college without really having a good pre-calc course, because I took one of these placement test deals when I got to the college, and it was multiple choice, and I'm good at problem solving, so I kind of did as well as I could on the placement test and answered stuff I really didn't know that much about because it was multiple choice and I could figure things out well. And I dropped into Calculus 1 without a good pre-calc background. So I kind of learned my trigonometry backwards, starting with the graphs of the functions, really the main way that you think about them in calculus, and then tracing back from there to the unit circle and how this stuff works from the more geometric side. And that was not traditional, but it worked for me. I'm glad that I had classmates that had better background in trigonometry because we worked together on F, and I learned how all this stuff works from there. So I know how important it is to have different ways of thinking about a trig problem and have the right picture pop up in your mind when you're doing something in trigonometry, to have that right idea in your head. Picture in here. There's actually a couple of different pictures of trig problems. So I'm going to grab one from the homework. Exercises is an example of that. Ask us to find an exact value. There's a little value to calculators in this, but there's a lot more value to the pictures. We want to see how both of these. This is from 6.3, number 44. It's kind of in the middle of what we're doing in the homework, but this is where I want to jump in. Draw some pictures of this thing. Find the exact value of each of the remaining trig functions. Sine, cosine, and tangent. And then there's also secant and cosecant and cotangent functions that are sort of reciprocals of these things. So we got to get used to that also. Each of the remaining trig functions of theta. And what we're given in this one is that cosine theta is 3/5. And it says theta is in quadrant 4. Quadrant 4. So they're pushing toward a unit circle understanding of this thing, and that's good. But quadrant 4 means that we're between 3π/2 and 2π. And I want to draw a couple of different pictures of what's going on here and understand what they're asking for. The exact value of each of the remaining trig functions means I want to know what sine of theta is. I already know what cosine of theta is. And I want to know what tangent of theta is. And I want to know what these other ones are. So I'm going to write them down. But we're going to come back to the other trig functions also once we get the 3 basic ones. So that goes down out of sight, but that's okay for now. We're going to start with the 3 basic ones and then see how those are connected. Cosine theta equals 3/5 needs to mean something for you if you're going to have the competence in trig that we want. It needs to mean something to you in a couple of different pictures. The function graph and the unit circle picture. I could actually answer this just from the unit circle point of view, so I'm going to think about that first. Then I'm going to tie it into the graphs of the trig functions thing. I got people watching over there. I haven't anybody. I don't see anything in the chat yet. We have a few people with us. That's good. So the unit circle in the xy plane looks like that. This is 1 comma 0 and negative 1 comma 0 and so on. Cosine on the unit circle is the x value. So when this function tells us cosine of theta equals 3/5, or decimal, that would be 0.6, 0.6. That means on this picture that x coordinate is supposed to be 0.6. So between 0 and 1, somewhere in there is 0.6. There's cosine theta equals 3/5. Looks like this. It's on that horizontal line, on that x value of 0.6. That means theta could either be in quadrant 1 or in quadrant 4, but we're told in this problem that theta is in quadrant 4. So there's usually two different places, two different quadrants that'll work, and this one must be the quadrant 4 version of this thing. That tells us some stuff also. So when you see a fact like this, cosine theta equals, and this is a positive number, then you should see this for a line right here has to be between 0 and 1, the value of it. You should see the two different quadrants, that it could be first or fourth quadrant, but we're after the fourth quadrant. So we're between 3 pi over 2 and 2 pi in radians. This is 360 degrees or 2 pi radians. So we're in between there somewhere. If your thought when you started with this thing was to solve for theta by doing inverse cosine of 3/5 in the calculator, that's good, but it's misleading there a little bit, because the inverse cosine function thinks all of these values should be in the first quadrant, and it's only going to give you the first quadrant version of that thing. We don't really need the value of theta. We need the value of these other things out there. So I'm going to do this without actually writing down what theta is, because I don't really need that. You could figure it out, but that's not what they're asking for. Cosine theta is 0.6, and that's the x value on there. We know that on the unit circle, x squared plus y squared equals 1. That's your 1 unit from the origin. So I can actually figure out the y. The y is the sine theta. So I can actually get that value from here. I know x is 3/5. I'm going to go ahead and do it in fraction form, because it wants the exact values. So 9 over 25 plus y squared equals 1. And that means, I'm going to make this somewhat readable here, y squared equals 1 minus 9/25. That comes out 16 over 25 when you do the subtraction there. So y squared is 16 over 25. And hopefully you remember your plus or minus when you see that. If I want to know what y is, I'm going to do the square root of that, but I'm going to get plus or minus. And the square root comes out nice. But this is plus or minus 4/5. This is where the quadrant thing helps us. We know we're in quadrant 4. So the y has to be negative. The y has to be negative 4/5 for our quadrant. Negative 4/5 is the one that's going to work. That's sine theta then. So that's the next part of my answer. Negative 4/5 is the y value. This is really having a hard time with this lighting. I know. Y is negative 4/5. So coming back to my question here, I got one other piece of this answer, but now I'm on a roll with this. I got negative 4/5. I know what that is. I'm just going to use the relationships between these things to answer the rest of the question. I don't have to come back to the unit circle for the rest of this now. I know the y and the x. And solve the rest of these things by the relationships that we have here. So tangent theta is always sine theta divided by cosine theta. It's y over x on the unit circle, but it's sine divided by cosine. So if I know those two basic ones, I can build the rest up. This is negative 4/5, and this is 3/5. So that simplifies to negative 4/3. That should be the tangent. -4/3. I'm going to try to write larger. And then the rest of these are just reciprocals of. All you got to do is remember what's a reciprocal of what to do the rest of these. So not knowing where people's trig background is at. I'm trying to review all the basic stuff, but I know I'm moving pretty quickly here. There's videos out there on this stuff, but cotangent is just the reciprocal of tangent. So if I have this value, I just got to do the reciprocal here. Secant is the reciprocal of cosine. So that's what I mean by the arrow there. That's the reciprocal relationships. That's 5/3. And cosecant is the reciprocal of sine. So that's just the reciprocal there, -5/4. All of those should be good from reciprocal relationships. So I got secant is 5/3, cosecant is -5/4, and cotangent is -3/4 from the reciprocals. Yeah, I'm not having much luck making this readable. I'm trying to say stuff out loud here, but I'm not having much luck with camera today. Not working with me. Now, I promised to do this looking at it two different ways. I want to think about what this is on the graphs because we're trying to introduce the graphs as we go along. So that was all sufficient to answer the question. We got everything we needed to get from that. But I want to think of this also from the trig graph point of view. We're going to be graphing these functions. And how does this, at least the beginning of this problem, look? We're given that cosine theta is 3/5 and theta is in quadrant 4. Wow, that is really kind of a video quality issue. I'm going to try to move slowly. But cosine is 3/5 and theta is in quadrant 4. What does that mean in terms of the graphs of the functions? Just in a little space, I'm going to fit this in. Your cosine function starts at the top. It's one of these wave functions. It goes through a complete cycle between 0 and 2 pi. So when I graph out this function, what was quadrants on the unit circle is not really quadrants anymore. It's these little pieces of it. This is where 3 pi/2 is. And I'm just in this habit of writing too small. I'm going to have to start getting some space and trying to write larger. But what was 4 before is the fourth chunk of this cycle. It's between 3 pi/2 and 2 pi still. Cosine is 3/5. 0.6 is the out there. So we see that's true in the first and fourth quadrant. We saw that on the unit circle picture. This is how it looks on the trig graph now. That since we're supposed to be in quadrant 4, we're talking about this theta value right there. So if you did inverse cosine of 3/5, you would actually get this answer, and it's not the right one for this problem. We're talking about value over here. But the rest of that can be thought through from there. The sine function looks like this. So, of course, the sine of theta, if theta is here, the sine of theta is going to be some negative number. That's how we got that. That goes with the fact that we got the -4/5 there. Graphs of the other ones are a little tougher, but once you know sine and cosine, you can build the others up. Well, I'm not going to try to draw the pictures of the other things. All right, I'm going to try to write larger and get a fresh start here. We're starting another problem here anyway. So going into the graphs, one 6.4, we're doing some transformations of the graph right here. We're supposed to look at these things. and get some stuff about the graphs from them. I'm going to look at 6.4, number 16. Just jump into this section there. And the instructions are to determine the amplitude and period of each function without graphing. Well, we could. I want to graph it also because we're trying to learn from it, but we'll see what the amplitude and period end up being and how that works here on a function like negative sine 1/2 x. Doing this thing without graphing, well, I don't need the picture to answer the question. What are they asking for? The amplitude and period for number 16. What is the amplitude? And what is the period of this graph? So for the regular graph of the sine function, amplitude is 1 and the period is 2 pi. It goes through a complete cycle every 2 pi units. So, and the amplitude is 1. So I'm coming back to the picture on that. The regular sine graph looks like this. 2 pi is how wide this thing is when it gets to the end of one complete cycle. And the amplitude equals 1. That's the amplitude on this thing. For the regular sine function, the amplitude is a vertical measurement and the period is a horizontal measurement. So they're going to be affected by stretching compression. That's the pre-calc way to think about these things, is in terms of what happens to stretch and compression of vertical and horizontal stretch and compression of this function. Vertical things are what happens on the outside of the function. So my vertical stuff is going to be affected by what's out here in the function. The value out here would determine the vertical stretch or compression. And that's just negative sine. That actually is a vertical flip. It's going to turn it upside down, but it's not going to stretch or compress it at all because it's -1. It's not stretching or compressing vertically. So my amplitude is still going to be 1. The amplitude is really the absolute value of this number. Since that's -1, the absolute value is 1. Amplitude is the same as the original function. Their amplitude is equal to 1. Horizontally, we do have something going on that's going to affect the period of this thing. When this number is less than 1, it's a horizontal stretch, right? F of 1/2 x would be stretching the graph horizontally by a factor of 2 right here. So the period is going to be twice as big as the original function. The original function had a period of 2 pi. This one's going to be 4 pi. We can get that by taking the original one and dividing by your stretch factor there, this number here, 1/2. Now in the book, they use some parameter values right there. So I don't want to get thrown off by the extra Greek stuff that you got going on in there. But they're using capital A and omega for these things. The capital A is on the outside, the -1, and omega is the little W looking thing that they have in the formula for that. That's this value. Period is always 2 pi divided by whatever omega is sitting there. So when that value is less than 1, we have a horizontal stretch, and we're going to get a bigger number. For the period, it's going to be longer. So I can do that without actually graphing the new function. But I also know everything about the graph for the new function. So even though this exercise said to do it without graphing, I want to graph it also because we're trying to see how these things connect. But what happens to the graph of this? And you could do the graph of that in the calculator easy, but I want you to see the connections between the base function and this. So my regular sine function goes up to 1 and down to -1 like that by the time I get out to 2 pi. It continues, but it's just more of the same. After that, that's one complete cycle. The -1, so if that's the graph of regular sine x, the -1 is going to be a vertical flip. The 1/2 is going to be this horizontal stretch. So it's going to stretch this thing out and flip it over. It's going to go down like this. And one complete cycle would go all the way out to 4 pi on that thing that's stretched out. So if you do the calculator graph, you should see something that looks like that. Continues through this way. It's stretched out, and it'll have a period of 4 pi. Amplitude is still how far it gets from the middle, so that's still 1 unit. Period is now 4 pi. That's the graph of, that's a sketch of the graph of minus sine 1/2 x. I'm going to jump ahead some on this in one of the other homework problems. Where they're asking you to find an equation of the graph. So here we're going to have to think back to what the equation is, to what happened to the graph to get to this point. I'm going to do number 62. I could do ones that aren't on the homework, but I figure I might as well look for the ones that I picked out there. So number 62. I'm going to duplicate the picture I'm looking at in the book here. The key values of that, at least. I'm seeing what looks like a sine wave. Continuing on out like this. And they've shown a couple of cycles of it, but okay. They're saying this is 2 pi right here. And it's marked off. This is 6 pi. These are the values they have marked on the graph, on the x-axis. And on the y-axis, this goes up to 4 and down to -4 on the y-axis. So that's your vertical values that happen to this. It's stretched out, vertical stretch to get to 4 and -4. And it's got a period of really 8 pi now, right? This is starting here. So it finishes a complete cycle when it gets back to this point, which would be between those at 8 pi. That's the period now is 8 pi. So it had a horizontal stretch and a vertical stretch done to it. It's a sine graph. It's not flipped, but it's stretched horizontally and vertically. So when I have multiple on the outside that comes from my vertical stretch was multiplied by 4 to get up to this. That value is going to tell me what E capital A is. And the value in here, that what they call omega right here, is, well, this was divided by. So they're saying that the period now is 2 pi divided by omega. Omega has to be a quarter for that to happen. That means if you multiply that over, 8 pi times omega equals 2 pi. So the value of omega has to be 2 pi divided by 8 pi. That's 1/4. That's often this fraction value like that. But I got 1/4 for that. That's the value in here in the function. 1/4 x is the thing that does your horizontal stretch on that one. So 4 times sine of 1/4 x is a good equation for this function. Calculator can confirm that if you want to. If you put this in as your function in the calculator and look at the graph, you should be able to confirm some of these values that it hits the top there at 2 pi and so on. You can check that. Make sure you're in radians. Make sure your calculator is expecting radians for everything that we do. We're not using degrees for anything. So it's all for the graphs. It's all going to be in radians. So make sure your calculator is set that way. That would be worth looking at. So trying to get a mix of these. I want to do one of the ones off from the lab. Lab's got some weird way of asking these questions, so I'm gonna jump in and get one of those into the intro that I'm trying to do today. The numbering's weird on the lab because I just selected a few of a bunch of problems, and that's what I had to work with. And the numbering's still off from original big list of problems, but number 4, which is the second problem on the lab, I'm going to take a look at that. So the cosine function is an even function and sine of x is an odd function. If you look at those graphs and think about the symmetry things that we were doing, you'll see even and odd in there. Use a graphing utility to graph h and use the graph to determine whether h is even, odd, or neither. There's some observations we can make off from that. They're asking you to do the graph, the calculator, and we'll make some observations back from there. But the basic functions, great example of even and odd. If you look around the y-axis, the cosine function is doing this. It's doing its mirror image on the other side right there. F of minus x is the same as f of x. That's what even function looks like. And sine is a nice picture of an odd function that it's doing something on this side and it's kind of doing the opposite here. F of minus x is the opposite of f of x. Symmetric about the origin, if you will. That was the graphic idea, even and odd. So which kind of symmetry do we see with these things? Let's take a look at that. So cosine squared x is always going to come out positive because it's a square, so or greater than or equal to 0. So I'm going to do cosine squared x. That's the fancy way of saying cosine of x squared. If I want the calculator to understand that properly, I'm going to go ahead and put that in as cosine of x in parentheses, and then my exponent outside of it. That's what the squared means, and that is you're squaring the value of the function. So they're going to be a little bit readable if I move it up a little. I would put that in as cosine of x squared. That's what cosine squared means. And I take a look at the graph of that thing. So let me see. All right. So detailed right there because I'm zoomed out too far. You can kind of see the symmetry on that, but I'd want to get a different window. I don't remember what the Windows settings were, but I'm going to zoom in a little bit on this. I'm not super good with the calculators here, and I haven't done this one an awful lot. But if you see too much and you want to zoom in on that, there should be ways to do that. So might not go closer a little bit. Let me see the symmetry a little bit more. I don't see that zooming. There's a symmetric graph right there. You see the same thing on the right side. It's coming down on both sides. Kind of can see that the range is between 0 and 1. what's happening on this side is exactly the same as what's happening on that side. That's an even function. So you can tell that. Now, that's all they're asking for on that, is that new function is an even function. Same thing with part B there, no? I want to go back to this and change it to sine squared of x. So clear that. Put in sine of x, e squared. Look at a graph of that. It's flat on either side. This is really small. And I don't know how the calculator works that well. Just zoom it in. But I do see the symmetry right there. It's symmetric about the y-axis. It's doing mirror image on either side. It's exactly the same on the left and right side. The squares are even. So this is also even. In general, right here, I want to point out something that's happening more in general right here, because symbolically what even and odd means. Even means f of minus x equals f of x. They're the same. And odd means if I do f of minus x, I get the opposite. If I'm going to then square this thing, if I square it, it's going to come out the same on either side anyway. So that tends to make things into even functions. If you are squaring a function, it's going to get rid of that opposite sign even if you had one. So it turns things into even functions when you square them anyway. That's worth looking at. What happens in here if we do an odd, something that started as an odd function times an even function? What is that going to do? We can look at a calculator graph to do it, but I want to do this symbolically also. See what happens. Symbolically, we're asking the question, how does it come out this way or that way if I do h of minus x? So think about what h of minus x is going to be here. And we're doing sine times cosine. So I'm going to do this one without the calculator just to think it through. But I know sine is an odd function, so I get the opposite of sine x using that idea. So I pointed at the wrong thing. Sine was the odd function. Cosine of minus x, that's an even function, so that comes out the same as cosine of x. What I ended up with then here is exactly the opposite of what I started with. H of x is sine times cosine. H of minus x ends up being the opposite of that, the negative of that. So that's what you expect from odd functions. So this ends up being an odd function. And if you do the graph of it, it should just confirm that. You should see the symmetry is about the origin instead. That ends up being an odd function. Or in general, if you're doing even times odd, you're going to get odd, which is not how it works with numbers. So it's not a great analogy for that, but it is how it works with exponents. That's really the right analogy for even and odd functions. If you think back to multiplying an even function by an odd function in terms of powers, you do end up with an odd function. So even times odd is odd. That's what happened here also. Those are nice. Nice to know things about that. Trig functions, as long as you didn't do some kind of horizontal shift to them, they're usually either even or odd. So that cuts down a lot of work on the graphing. If you can graph one side of it, you know what the other side looks like if it's an even function or an odd function. So that's useful to do. Number 12 down here is a much more triangle-based question, and I haven't done triangle trig. Well, I'm looking at unit circle and function stuff mostly, but we don't want to forget about triangles also. So let me at least get set up on that one for today. Get you started on this thing if you don't see it right away what's going on here. An escalator in a department store is 50 feet long and carries customers through a vertical distance of 20 feet. So from one floor to the next is 20 feet up. But it's 50 feet long. That's the diagonal length of the escalator. So I guess my picture is the overall picture of this thing is it's going 50 feet with a vertical increase of 20 feet. So I don't really know the horizontal on this, but there would be some right triangle right there. And that's the angle that we're talking about. The angle that the escalator makes with the floor, that's between here and there. So back to right triangle way of thinking about this. I need the theta when I know the opposite side from the angle is 20 and the hypotenuse is 50. So your trig definitions in terms of the triangle, the opposite and the hypotenuse, that ratio would be the sine of theta. So this triangle picture would tell us that sine of theta is 20 over 50. And this is a nice first quadrant angle. So doing the actual inverse sine of that thing is the right way to go about it here. We are talking about a first quadrant thing, so there isn't any problem with the quadrants there. You can trust your inverse sine button when you do that. So do the inverse sine of 20 over 50, and it'll give you an angle that's there. We got to get used to radians. So right now that's going to come out as a radian measures something between 0 and pi over 2. In that first quadrant, this is actually pretty low angle, probably so less than 1 radian. And if you're in radian mode, your inverse sine of 20 over 50 is going to come out in radians. That's good for what we're trying to do now. That is the angle. It's just the angle in radians. We don't need the degree measurement there. If it takes 25 seconds to carry a customer from the bottom of the escalator to the top, how fast in feet per second is the escalator moving? Well, the escalator is on the diagonal right here. We're talking about the movement on this. So it's covering 50 feet from bottom to top. And it's telling us that that takes 25 seconds to do that. So the units help you out there. If you want that in feet per second, that's 50 divided by 25 is just 2 feet per second of actual movement right there. We could actually work out the separate pieces of how fast it's moving vertically in feet per second, or if we figured out the third side of the triangle, we could talk about how fast it's moving horizontally. But the actual movement of the escalator is the diagonal there, so we're using that hypotenuse length for that. So if you haven't really locked in all of those transformations of the graph yet, as far as stretch and compression and horizontal and vertical shifts, all that is really the key to a lot of these trig graphs. We remember the basic ones, and then we build up these other trig graphs from that and from the transformations that go on. But there is one sort of new thing. You might not have messed with these secant and cosecant and stuff, and those are reciprocals of something. So here's a way of thinking about that I hope helps. In general, what happens if we take the reciprocal of a function? What does that do to the graph? So I'm going to start with a familiar algebra example. And then do one of these trig examples of what happens to a reciprocal function. So I'm going to end up doing cosine of x and using the graph of that to help me graph the reciprocal of cosine, which is secant of x. That's 1 over cosine of x. Using graphical ideas about this thing that we did. I told you rational functions were my favorite thing. That's definitely true here. So I want to compare this to what happens when I have y equals 3x plus 1. So regular graph of a line with intercept 1 and slope 3. So that's going up like that, 3, 0, 1, through 1, I'm sorry, 1/3. Negative 1/3, comma 0 would be this intercept on it. 0, 1 would be the y-intercept and so on. This function, what happens if I do the reciprocal of that? 1 over 3x plus 1. So I want to make a connection back to everything that we did with rational functions right here. If I try to do the graph of this using our rational functions idea, I know some things. The numerators never equal to 0, so I get no roots of this function. I get no x-intercepts. Okay. The denominator is equal to 0 at negative 1/3. We just went through that. So that negative 1/3 turns into a vertical asymptote. That's where the vertical asymptote is going to be. That's multiplicity 1. So this is going to follow that vertical asymptote. And the degree is bigger on the bottom, so it has a horizontal asymptote at 0 also, and it's just going to follow that thing. The y-intercept is 1 over 1, so it still goes through 0, comma 1. The graph goes through 0, 1. That really tells me everything I need to know, because if the graph is up here and it has to follow that vertical and horizontal asymptote, it has to do this. And since this is multiplicity 1, the other one's got to be on the other side. You get no crossing points because this function is never equal to 0. So that's the graph of that. Look at what happened. Doing the reciprocal here is the 0 there becomes a vertical asymptote. I'm going to write it out because it's not like the number 0. But the 0 of the function becomes the vertical asymptote. And the place where the function was equal to 1, well, the reciprocal of 1 is 1. So we got that same value where it's equal to 1 right there. Think about how reciprocal works now. Whenever y is less than 1 on this thing, in between that little piece, the reciprocal of it is going to be greater than 1. The reciprocal of a small number is a large number. So in this little piece in between there, the reciprocal is going to have values bigger than 1, and vice versa. If y is bigger than 1, the reciprocal function is going to have less than 1. So this part that was above 1 becomes this part that's below 1. That's what happens with reciprocals. And similarly, on the negative side, if it's between negative 1 and 0, it's going to get flipped out to be less than beyond negative 1. And if it's beyond negative 1, it's going to be closer to 0. So this sort of gets turned inside out. The 1s stay the same because the reciprocal of 1 is 1. Wherever this was less than 1, this is bigger than 1. Wherever this was bigger than 1, this is less than 1. And the same kind of thing on the negative side. So using those ideas, you get a lot of stuff about the trig graphs from it. So here is my basic equation, graph of a cosine function. This is pi into pi. The So those are some of the key values here. This is 0, 1. When I go to do the reciprocal of that, I'm going to use those same kind of graphical ideas. That the zeros of the trig function, the zeros of the original function, become vertical asymptotes over here. So that's at pi, 2 pi, also over here at negative pi. I got vertical asymptotes now. I graphed the original function wrong. That's why this is looking wrong over here. I made a mistake on my original function. We should be back to the top by the time we get to 2 pi. Okay, this is a terrible enough start that I really want to start over because I messed up my cosine function so badly. I'm not even going to be able to fix it. Start over on that. Sorry, I need to wrap this up in a few minutes, but let me draw what the cosine function really looks like and try that again. Here's what y equals cosine of x really looks like. Starts at the top, comes back to the top at 2 pi. This is where 2 pi is, pi. So, sorry about that. I messed that up badly. The intercepts, or the zeros of this thing, are at pi over 2 and 3 pi over 2, and minus pi over 2, and so on. Those are the actual intercepts that become vertical asymptotes. So when I go to do secant function, I'm really kind of turning this inside out. What was the zeros before becomes vertical asymptotes. Pi over 2, 3 pi over 2 become the vertical asymptotes. Where it was equal to 1 before, it's still equal to 1. Reciprocal of 1 is 1. These points. And the reciprocal of negative 1 is negative 1, so it's still at negative 1 here. But where it's less than 1, this one's going to be greater than 1. And where it's between 0 and negative 1, this is going to be below negative 1. It gets turned inside out this way. Between 0 and negative 1, the reciprocal is between negative 1 and going down to follow the asymptotes. So these are going to follow the asymptotes like this and continue that out. So you get values that are always outside of 1 and negative 1, or the secant function. So these other graphs, you can get the calculator to do them, but you should see that one as the reciprocal of the cosine function. You should be able to compare them that way if you think about how this graph looks. The reciprocal graph would just be kind of flipping this thing inside out. That's one way to look at it. Okay, I've got to get set up for the next class here, so continue sending questions as you get to them, working through that homework. There's a lot of variety here of exercises, so see what makes sense to you and let me know what doesn't make sense to you. I'll try to get answers back to people either by email or in the Blackboard discussion. As you go through the work, let me know what you're having trouble with. And have a good week.